So hot oil with a given specific heat is cooled by water in a 2-shell pass, 12-tube pass heat exchanger. The tubes are thin-walled and are made of copper with an internal diameter of 1.8 centimeters. So already we see the same tip as before. Thin-walled, right? So, and of copper, which is a material that's very thermally conductive. So this is saying, disregard the conduction, the resistance due to conduction because of the tube. Also thin-walled. The outside area of the tube is very, very similar to the inside area of the tube. The length of each tube in the heat exchanger is 3 meters. And this is going to go back to one of your questions on the previous problem. So this is for each tube. Watch out, right? So for each tube, we have 3 meters in length, and we have a total of 12 tubes. So if I were to stretch the whole thing, what I would have is 12 times 3 meters in length in total. The overall heat transfer coefficient is 340. So is this U or is this H?
Then that's U.
That's you.
Right on. Good on you. And then water flows through the tubes at a rate of 0.1, and the oil flows through the shell at a rate of 0.2. The water and the oil enter at temperatures of 18 and 160 respectively. Determine the rate of heat transfer in the heat exchanger and the outlet temperatures of water and oil. All right, so first things first. I'm going to draw the same thing as before, okay? So I'm going to draw the same simple system to simplify our analysis. On one side, I'm going to put the hot oil, or actually, which one are you trying to heat up? Hot oil, and the other one the cold water. So we have hot oil and cold water. On the NTU method, it doesn't matter whether you put them in parallel or in parallel flow or counterflow. It doesn't matter because we're not taking the delta T log means as before, right? Instead, we're interested in the NTU, which it uses a different method. By the way, you can actually have, for instance, hot going this way and cold going this way. So it doesn't even make sense to have this talk about parallel or counter in this on the NTU method. We do know the inlet and the outlet of the different things. We do know the inlet of the hot and the outlet of the inlet of the cold. We know the hot is coming in. Let's do hot going this way here. Let's do cold going this way here. Again, it doesn't matter, okay? 160 and 18. Okay, which way is my Q going? From top to bottom, from bottom to top?
Top to bottom.
Good job. Yep, you don't think about that. We know that. Brilliant. Okay, what else? We know the mass flow rate of each. We know the mass flow rate of the oil. So the mass flow rate of the oil is given as 0.2 kilograms per second. We know the mass flow rate of the water is given as 0.1 kilograms per second. And again, know that I'm doing this all in the same line, keeping the system. We also were given the specific heat for the two things. So specific heat for water and oil. Specific heat for oil was given as 2200 joules per kilogram Kelvin. And for water, it was given as 4180 joules per kilograms per Kelvin. Yep. So that means that if I want to find my heat capacities, like I told you before, all I need to do is multiply these two guys here. And that's another reason why I keep them all in the same line. Okay, so you're not mixing up these when you're doing it. Okay, I'm multiplying this by this and this by this. This one is very obvious. It's 418. And let's do like this. Heat capacity. Oh, come on. Heat capacity. 418. Unit wise, we get rid of both of them. We get rid of the kilograms, so kilograms per second, joules, kilograms per Kelvin. Yeah, and that leaves us with watts per watts per Kelvin, difference in temperature, or joules per second for difference in temperature. You can choose whatever you want to put here. Let's do watts. And on this side here, we're going to have the same thing, except this is going to be half 0.2, so it's 440 watts per Kelvin. Okay, and until this point where I calculated both of them, I don't know which one is the minimum and the maximum heat capacity. But now that I calculated, I know, and it's as simple as see which one is greater. That's all I'm doing. Okay, so hopefully see this one is greater than this one, so that means that this becomes my heat capacity minimum, and this is the maximum heat capacity I have in my system. Okay, so until you calculate, there's no way for you to know. Now, what do? We are asked, let's go back to the question. We are asked to determine the rate of heat, so that is, what is the Q? the outlet temperature of the water and the oil. So what's the temperature outlet of the hot? What's the temperature outlet of the cold? Okay? In simpler times, what we would do is, we would have both of these, so we can calculate one of them, use it to calculate the other one, and that would be all good. But now we don't have everything, so we're gonna have that's what we're gonna use the NTU. And note how this is more of a realistic problem, right? Because you know the things that you're putting in, but you want to be able to determine what's going to come out. And then if it's not good enough for you, you can go back and tweak and mess with areas and all that, right? So to do that, what I want to do is I'm going to use the NTU method, the number of transfer units, which is related to, as this equation is telling you, the number of transfer units is related to the surface area, the overall heat transfer coefficient, and the heat capacity, the minimum heat capacity. Okay, what's the idea here? What's the game plan? Well, if I can find these three things here, I can find the NTU. If I can find the NTU, the number of transfer units for my given heat exchanger, I can use this graph to find what is the effectiveness. Okay, so again, what is the effectiveness? How the actual heat transfer that I get in respect to what I could get on the maximum, right? The maximum theoretical I can get. If I can find that, then I can find my actual. If I can find my actual, that eliminates this problem. Once I have the Q, I can find these two guys easily because we know how to do that, right? So let's lay down a game plan here. I want to find what is my effectiveness, right? What is my effectiveness? Actually, do it by steps. I want to find out what's my surface area because I don't know yet. With that, I can find my NTU. With my NTU, I can find my effectiveness. With my effectiveness, I can find my Q actual. With my Q actual, I can find the cold outlet and the hot outlet. Okay, that's our game plan. Let's start with the surface area. We were told we have 12 tubes, and that each of them has 3 meters in length, and the diameter of them is 1.8 centimeters. So that's very straightforward for us to find that area. The surface area of a tube or a cylinder will be 2 pi r times its length. Yeah, that's for one of them, right? So if I want the full surface area for this heat exchanger, so for the whole heat exchanger, so the whole heat exchanger, what I'll be doing is my surface area will be 12 times my 3 meters, right? I have 3 meters each with a length of 3, times my 2 pi, times my r, and my r is going to be 0.9, right? 0.9 centimeters, or 0.9 times 10 to the minus 2 meters.
12 times because 12 two passes, right?
Yes, that's correct. And because each of them is 3, right? So note how this is different from the previous question, in which it said the total length is 60. This is telling you that each tube is 3. So watch out for that. What does this turn out to be? About 2 meters squared, that is. This is meters squared because I'm multiplying 3 meters with 0.9 meters. So this is from the radius, this is from the length of each tube. And I get the 2 meters squared. Okay, so that's what I was missing to be able to calculate the NTU. So the number of transfer units will be the 2 meters squared times my overall heat transfer coefficient that we were given in the start, and that's 340. And then my C min that we found out to be 418. This turns out to be, what did I get? About 166. So you have about 1.66 transfer units in a heat exchanger under these conditions. Unit-wise, we have meters per second, meters squared on the area, watts per meter squared per unit of difference in temperature and the overall heat transfer coefficient. And here on the C min, we have watts per difference in temperature. Okay, so watts and watts, meters squared, difference in temperature. So there's no units for the number of transfer units, right? So literally, it's the number of transfer units. It's not, a physical quantity. Beautiful. So now we have that. We can read it off this bottom graph here, 1.66. If this is 1, this is 2, this is going to be my 1.5. So my 1.75 is going to be somewhere in the middle, and then my 1.66 is going to be somewhere around here. Okay, note this is not an exact science. If you have softwares and all that, it's they spit out for you automatically. But when we're using graphs, that's going to be the best as we can do. The other thing I'm going to need is my second parameter to be able to read off this graph, which is the ratio between my C min and C max. Now that's very easy for us to obtain because we already have both of them here. So we can do the ratio between C min and C max is just 418 divided by 440. which turned out to be 0.95. And this is what we need to be able to find what's the effectiveness of our system. Okay, so 0.95. Let's once again draw our, got my ruler here, try to draw a straight line on the tablet. All right, we have 0.95, so we know that has to be between 0.75 and 1. Between the two, I have this distance here. Right down the middle would be the mean. 0.95 has to be way closer to 1, right? So about there. Let me go ahead and draw a horizontal line there from that point to my. Okay, so again, if you guys did this already, you could check whether you read it correctly. If you read anywhere between 59 to 61, you're probably safe. Let's go ahead and use the 60, which is right where we landed. And then that means that 60% is our effectiveness, right? So going back to the definition of it, right? The maximum theoretical of all the energy I could transfer, I'm only able to transfer 60% of that. And that's going to be my actual. So that means, let's write that mathematically. My effectiveness is just the ratio between how much I actually got divided by how much I could theoretically get. So therefore, if I want to find out what is my actual, I need to just multiply the effectiveness by the maximum theoretical. All right, one thing important that I forgot to tell you, obviously we only have one graph for this problem, so it's very straightforward, but in general cases, what we need to find is what is the correct graph, just like on the previous question, right? So this is the figure for the NTU for a 2-shell 4A12 tube passes, so any multiple of 4. In our case, we have 2 shells and 12 tubes, so all good. We can green tick here, and this is the correct graph to use. But in reality, what we would have is like you have maybe 3 to 4 or 5 graphs in an assignment or in an exam, and then you have to choose the right one. In real life, you can either use a software or even have a book full of different graphs to choose from, and then you have to find the right one. Okay, so we found this fellow here. We're happy about that. All we need to do now is find the maximum heat transfer so we can find the actual one. What is the maximum possible heat transfer I can get? Well, the maximum possible heat transfer I can get, and this again goes back to your lecture, is the minimum heat capacity times the maximum delta T, the theoretical maximum delta T. The minimum heat capacity we already know. The maximum delta T we know as well. Why is that? Because the maximum delta T in this problem is related to the information that we already have. Think about it with me. As my hot is going through this heat exchanger and it's leaving on the other side, its temperature has to be something smaller than 160. Right? Let's say this is a horrible, horrible, horrible heat exchanger and it leaves at 159. Likewise, this guy, as it's going through the heat exchanger, it's gaining energy, it has to be heating up, right? So again, it's just for the sake of argument to say this is horrible and just 19. Even so, even if it's that bad, the maximum delta T I can have in this problem is between the inlet of both the hot and the cold fluids, right? And that's always going to be the case. Whenever you have a heat exchanger, the difference between the inlets of the two fluids that are exchanging heat will always be the maximum delta T you can have in the system. Regardless, and this does not matter whether they are on the same side or, like I said, if they are perpendicular to each other, that does not matter. What matters is that the absolute quantity, right? And that's why it's a theoretical maximum. So going back to this, my Q max, the maximum theoretical I can have, is my C min, which we found to be 4.418, times my delta T max, which is 160 minus 18. This is going to give me a huge number of 35,000 or so. 35,613.6. Sorry, 613.6. And then unit-wise, our 400, that's the C min, that's what we found to be watts per difference in temperature. And then we have a difference in temperature in Celsius, which can be the same thing as difference in temperatures in Kelvin. Okay, so this is watts. Obviously, this is a big number, so we can 1, 2, 3, 35.6 is probably more appropriate here. Okay, so this is the maximum. Oh, sorry. My bad. I put the wrong figures. 59,356. Back me up, please. I skipped ahead.
Yep, that's better.
Okay, perfect. Thank you. Okay, so that's a maximum theoretical. You already know what's coming, right? What do you think 60% of this is? Well, 60% of this is the 35 that I just wrote down. So if I want to find my actual, I just need to take 60% of my maximum, which is the 59,356, and now I can go back to the value I gave you guys before, the 35,613.6. Right? There's no units here on the effectiveness and the ratio, so there's no units there, so we'll just keep the units of what we had before. And now we can say it's 35.6 kilowatts. Okay, you guys happy with this?
Yeah, it seems pretty all right.
Yeah. Yeah, because
Follow the plan, do the things.
once we get to this point, it's like, okay, now that we know the Q, then we go back to week 2, week 3, things that we already know how to do. Because now we know the amount of energy both fluids, the hot fluid is given away and the cold fluid is absorbing, and then find out the outlet temperature. That's straightforward, right? You know how to do that. So there's a couple of options now on how to solve it. I'll lay down a couple here. Let's start with the hot one, I think. Which one is the one for the minimum? The minimum one is the hot one. Yeah, okay. So let's start with, no, sorry, the minimum for the cold one. Yeah, cold one. Let's start with the cold one, just for the sake of simplicity. What is the energy the cold one absorbs? Well, that's the actual energy that was transferred in a heat exchanger, what we just found out. And we also know that's related to C, mass flow rate of the cold, the specific heat of the cold, the delta T of the cold, and all of that. Now, something interesting happens here. There's two options, all right? You know this value, so you can plug this in this value and find out what is this delta T straight off the bat, like we always do. But there's another way you can do it. So let me put down both ways. First way is, we know this is 35,613.6 watts. We know the mass flow of the cold is 0.1. We know the C sub P of the cold is 4180, and that's going to give us the delta T of the cold. The delta T of the cold has to be, which one is greater? This one here or this one here? The right one or the left
I'm assuming the right one's greater.
You have to assume, you can be sure, right?
Yeah, for sure.
Yeah, you can be
Heat's flowing into it.
That's right. Yep, that's right. So that means my delta T on the cold is going to be my T cold out minus my T cold in. So my T cold out minus 18. My T cold out minus 18. Okay, and the only unknown is T cold out. T cold out happens to be about 103.2. Okay, that's one way to do it. Something interesting happens though. Let me copy this and show you another way you can do it. Because you have all these different relationships that you developed as you were solving this, there's something else you can do, because you know that this Q actual is actually 60% of the maximum theoretical one. So that means that, what do I want to do? I want to eliminate this and this. Okay, so that means I can write the Q actual as 60% of my Q max, which is C min times delta T max. And it just happens that this guy is our C min, as we found out before. So you can do this, and you can have a simpler relationship, I guess. 60% of my delta T max, which is 160 minus 18, has to be equal to the difference for the cold, which is T cold out minus 18. Okay? And that obviously is going to output the same exact answer. Cold out has to be 103.2. Unless I did any mistakes along the way. Why do we care? Well, two reasons, right? First reason is, well, you can choose which one to do when you're solving this. Second reason is, if you are doing this for an exam or assignment, for instance, that's a way for you to check your answer. They have to be exactly the same according to everything we've done so far. And then for the hot, same thing, right? So the hot, we can do whichever method you wish. So Q for the hot has to be the same Q that's being exchanged in the heat exchanger, which has to be the mass flow rate of the hot times the specific heat of the hot times the delta T for the hot fluid. In this case here, 35,613.6 has to be equal to the mass flow rate of the hot, which is 0.2, specific heat of the hot, which is 21, I forget what was that, 2200, and then we know for sure that this one here is greater than this one here, so 160 minus the output of the hot. to 160 minus the output with hot. T hot out. Right, so that means my T hot out, this would be equal to 79, about 79. So that is the last piece of the puzzle. Now you can do the same thing here. Analogous to this, you can do this for the hot if you wish. I'll leave that for you guys. It also has to render 79, obviously. Questions from your end?